The Baryon symmetry of the universe, so-called the BAU, can be obtained from the by using the formula of number density of the baryon and the number density of the photon. There are two ways to define the BAU. The first way is the baryon to entropy relative. Because the number densities in the expanding universe changes during the time, the matter-like component number density is proportional to the 8 to the minus 3, whereas the scaling factor. So the 2 makes the some invariant quantity along the cosmic time. If there is specific process, then we should divide to the other quantities. So the number density can be divided to the entropy density, that's the first way, and the number density of the Baryon symmetry can be divided by the photon number density. Because the such entropy density and the photon number density is a difference, so the difference with the order of the term, so the Baryon symmetry is delta V, baryon to the entropy ratios, and the baryon to the photon ratio delta V is the difference to the order of the term, but it's almost the order of the 10 to the minus 7 or 10 to the minus 11. And today, I will derive the number density and the entropy density to obtain this value. And also I will discuss about some related topics like as energy density and the Lambda symmetry by using the chemical potential. So first of all, the number density can be obtained by the integrations of the distribution functions over the phase space. So here is a distribution function up. Sometimes it includes a degree of freedom, Z, and it integrates sort of as a phase space. In the Bose-Einstein's statistic case, the distribution functions are given by the 1 over the exponential E over the t minus 1. And we'll assume that the chemical potentials are equal to 0 in this Bose-Einstein statistic. And we will consider the relativistic case. So the temperature is larger than the mass. And by using the spherical coordinates, the phase space momentum integrations can be changes by the directions with the angular component. And in the relativistic case, we'll use the following integral formula by using the Zeta's functions and the gamma functions. So by using this formula, we can obtain the number density for the Bose-Einstein statistics in the relativistic case. So the number densities are given like that. And we will change the variable. First of all, the m over the t as x and p over the t as zeta. And in our case, this is relativistic, so x goes to the 0. So by using this formula, the zeta function and the gamma functions turns out. And by using the property of the gamma functions related to the factorial, the number density for the such Bose Einstein statistics particles given like that. So n equal to the zeta series over the pi squares gt cube. So this number densities will be used for the photon. So in the photon case, the degree of freedom is 2 because it's the mass loss. So there are 2 polarization states. And the number densities are proportional to the t to the 3. And the temperatures are proportional to the 1 over a. So is proportional to the a to the minus 3. So number density is the decrease over the cosmic time because of the universe expansion. Similarly, we can obtain the number densities for the other cases. For example, in the Fermion case, the distribution function given by the Fermi-Dirac statistics. And the Fermi-Dirac statistic, the signs are changes in the denominator. Also, we will apply the relativistic case and the chemical potential is equal to 0. We will generalize this case for the non-relativistic case and the non-zero chemical potential light. By using the integrations again, and especially in this case, the denominators assign the changes for the last term, so that we will divide the two fractions to use the same integration formula. So that there are two terms, and this gives the additional factors of the Fermion case, so that there are two terms from the two different fractions. So this parametric statistic fractions are decomposed to two fractions, and this gives the two terms. And as a result, there are additional factors 3/4. So the number density for the Fermion case in the relativistic limit, there are additional 3/4 factors, and other parts are the same. So we will insert these 3/4 factors for the Fermion case in the relativistic limit. Now that we'll consider non-relativistic limit. In the non-relativistic limit, mass is larger than the temperature. And in this case, the Qc, which is P over T, is a lot smaller than the X, which is M over T. So that there are we cannot ignore the X, so that we can expand this exponential factors in the denominator. So there are some of the calculation processes, expansions in here, and by using this property integrations formulas for the gamma functions, then we can obtain the results of this integration. And as a result, there are still the remaining factor of the exponential minus x. This comes from here. So we just integrate over the Qc here. So the exponential minus x gives the Boltzmann subtraction factor. So in this case, the statistics that follows the maximum Boltzmann statistic, and this exponential gives the Boltzmann subtraction factor, which is exponential minus m over t. And there are still the number densities are proportional to the t to the cubes. So the final results are given like this in a non-relativistic case. So also this number density for the non-relativistic case will be used in like this many times. There are still degrees of freedom and proportional to the t to the derivative 2 because there are additional x is m over the t here. So and this is in the dimensional lattice the same with the to the 3 because this is 1 over the volume. So this is the same. And also there is partially there are Boltzmann subtraction factors up here. So in the non-relativistic case, the mass is rather than the temperature. So these factors are surplus in the number density. So when the mass is rather than the temperatures, the number density is extremely small. So actually we can do the number densities over the cosmic time, like the jet as m over the t. This is not lab shift. And when the jet is rather than the 1, the number density is in this equilibrium cases are strongly surplused in the Boltzmann subtraction factors. And when the jet is extremely larger than the 1, the number density can be ignored. Now that we can calculate another density, the difference thing is the distribution function should be integrated with the energy over the phase space. So there are additional factors in the numerator. And the techniques are also same. In the relativistic case and the Bose statistic, we can take the limits of the x goes to 0. And by using the same integrations techniques, we can obtain the formulas for the analysis in the Bose statistic and the relativistic limit case. The different thing is there are analysis proportional to the t to the 4 in this case. So this is the proportional to the a to the minus 4 in the Madeline case. So this is the same result with the Friedman equations. And the factors are also different. In the previous case, number densities in the Bose statistic, there are such a function, but the factors are different for the another density. Similarly, we can obtain the another density for the Fermions in the relativistic case. The different thing is that in the denominators, the last term has a different sign. And as a result, we also decompose these fractions over time. So there are two terms, and this makes additional factors in the Fermion case, step over A. In the non-relativistic case, the energy densities are just like given like the m times the n, because in this case the energy is similar to the mass because of three momentums are almost negligible. So if we multiply the mass and the number density, then we can obtain the energy densities in this case. So we can get the total energy densities of the universe. There are the relativistic effective numbers of the degree of freedom, which is defined as this star. And the non-relativistic case, they it will be negligibly small. We'll ignore here. In the boson case, there are just a degree of freedoms, but in the Fermion case, there are additional 7 or 8 factors that multiplies. And also the particle species I, some particle species can be decoupled from the equilibrium. So the equilibrium temperature T, in this case, the photon temperature, and the particle species temperature Ti can be different. So we choose the corrected additional factors as a light year sort of the temperatures. Now the finalist case. Now I will talk about the non-zero chemical potential case. In the chemical potentials, for the following is the reaction formula: H plus B goes to the C plus D, and there are inverse process. The chemical potential should satisfy these formulas for the original particle species and the final state. And if we consider some photon radiations from the KD, the chemical potential for the photons equal to 0 is also constant with the Bose-Einstein statistic. And for the particle and the antiparticle case, they are analyzed to the two photons. So the chemical potential for the photons equal to the 0. So the chemical potential of the particle shift the minus sign for the chemical potentials of the antiparticle. So now we will not ignore the chemical potentials. And for the number density for the antiparticle m bar, the signs are different for the chemical potential. So the minus mu becomes a plus mu. So if we consider the difference of the number density for the particle and antiparticle, so the m minus m bar, then there are two terms. For the particle, there are minus mu, and for the antiparticle, the chemical potentials are a different sign. And then we'll consider the Fermion case. Because for the photon case, the antiparticles are same, but in the Fermion case, the Fermion and antifermions are different. So now we change the variables again with the coefficient x. Now the x is here the mu of t, not m. We'll consider relativistic case. Also, we can generalize the non-relativistic case without the ignoring sort of the mass parameter. Now we'll define the new parameters of the y, and there are some of the many integration regions, some calculations, and some decomposition. There are some of the basic algebra. Then we can obtain the difference of the number density for the fermions and antifermions as the functions of the chemical potentials mu over the t. So the finals are just like given like that. So the difference of the number densities for the particle and antiparticles functions of the chemical potentials. So if there are the non-zero chemical potentials, the number density for the particle and antiparticles are different. So by using that, we can obtain the formula for the Latour symmetry of the universe. We will discuss it like this. So all the ingredients and the formulas are ready. So now we will induce the Latour symmetry first by using the previous formula. There are some issues around this, some images. The Latour symmetry is eta L that defines as the ratios between the number density for the lepton and the anti-lepton difference over the number density of the photon. And in the numerator case, it can be expressed by the general parameters with mu over the t. Mu over the t is defined the QC in here with the chemical potential. So in the numerators, we will use the previous formula. And for the denominator, we can use the number density for the photons. So there are QC some zeta 3 of the pi square, and the degrees of freedom the 2, and the T gamma 3. And in this case, the lepton temperatures and the proton temperatures are different. Because we consider some of the neutrino temperatures in here, and the neutrino temperature and the proton temperature are different. Because there are electron positrons that are in relation to the photon, and the photon can be hit by this such annihilation process. So the temperatures of the photons are different, and the neutrinos are already decoupled in the high temperature. So the neutrinos are out of equilibrium, but the photons are in the equilibrium. So these processes occur, so the photon temperatures are different. So such a light years of the photon temperatures and neutrino temperature can be obtained by using the relativistic effective degree of freedom, such as star. In this text, we will discuss the entropy density. The entropy density is small s is a low plus p over the t by using the thermodynamics of formalism. So by using that, the entropy density is just proportional to the t to the 3. The difference is just energy density is proportional to the t to the 4. So there are same degree of relativistic effective degree of freedom, G star, but we should be careful for this additional temperature factor. The temperatures, the entropy densities are proportional to the t to the cube, so that the temperatures factor should be different. So but we know that the total entropy of the universe is a constant if there is no additional process. So the entropy density times the scaling factor should be same. So entropy density is proportional to the effective degree of freedom for the entropy case, G star S times the T cube. And when the temperature is larger than the electron mass and the lower than the electron mass, this effective relatively effective degree of freedoms are different. When the temperature rather than the electron mass, the electrons are still relativistic, so it includes in this effective degree of freedom. So there are electrons contributions, so the G star is equal to the 11th over the 2. But when the electrons become the non-relativistic, the effective degree of freedom becomes the 2. So the initial photon temperatures are same to the there are the 11th of the 2 factors, but this is the constant when the neutrinos are decoupled, but the photon temperatures hit is by the electron position annihilation, but the effective degree of freedoms are 2. So the light year between the photon temperatures and neutrino temperatures has there are additional 4 over the 11th with 1 over the cube value. So we choose the instance of these factors of the Laplace matrix formula. So by using that, we can obtain the formula for the Laplace matrix at L as a function of the degenerate factors mu over the t. And these degenerate factors currently is measured by the M+6 experiment in 2022. So there are some of the constraints, some of the 0.95 confidence level, and some of the 9 confidence 1 sigma 2 sigma. So the y-axis is degenerate factors, and the x-axis is effective numbers of the relative species. So delta n. And the QCs for the degenerate factor for the electron neutrino is around 0.05. So by using that, we can obtain the eta L Laplace matrix, which is ordered by the 10 to the minus 2. Such as the degenerate factors of the electron neutrinos can be measured by the helium-4 abundance. So we already derived the number density for the non-relativistic case. So in the non-relativistic case, there are some of the still the Boltzmann separation factors and also the degenerate factor. And the helium-4 are non-relativistic. So the helium-4 abundance are related with the degenerate factors. And also for the relativistic factors, the degree of freedoms, some of the neutrino species that delta n's are also related, so that we can beat the delta n and the cases mu e's by using the helium-4 abundance. In currently 2020 M+6 experiments, an extremely metal force representation exposed by the several survey by using the EMPZ, such a galaxy some specific kind of galaxy, we can measure the helium for abundances, and we can calculate the Lawton symmetry of the universe. So now the remaining part, I will talk about the baryon symmetry of the universe. Already I say that there are two different definitions of the baryon symmetry of the universe using the entropy density and the photon number density. So the ratio between the delta B baryon to the entropy ratios and the baryon of the photon ratios can be converted through between each other by using the ratios or the Gamma. So already we know that the photon number density and the entropy density. So there are 0.14 factors between the delta B and delta B. Such eta B can be measured by the BBN or CMB. So in the BBN, we can use the non-relativistic number density here. And yeah, I will skip some here for the BBN. So there are some of the formula for the BBN. The ratios of the neutron and the proton and the helium for abundance can be obtained from the number density for the proton, neutron, and the nucleon. And by using the chemical potentials relations and also by using the binding energy and the mass fractions, we can obtain the Saha's equations. And the final results are given if there are some specific kinds of nucleon A, the mass fractions of A, XA can be given by the other quantity. And especially there are eta B, which is the baryon symmetry of the universe. And this eta B is extremely small, 10 to the minus 10. So that this makes the this factor, exponential factor, should be the large. So this is the small. So to give the large XA mass fraction almost 0.9 when the BBN circle, this exponential factor should be large. Is to mean that the temperature should be larger than the temperature should be the smaller than the binding energy. This binding energy is known as almost some mega electron volt for the nuclear physics MS scale, but the BBN temperature is 0.1 mega electron volt, so slightly smaller than the nucleus physics scale. So by using that, we can measure the eta B. So in this today's we talk about how can we obtain the formula of the number density in the Fermion case and Bose case and the relativism and non-relativistic case and the zero chemical potential and non-zero chemical potential. And by using the formula, so the density and non-zero density formula, we can obtain the formula for the baryon symmetry of the universe and the Lawton symmetry.